Okay, so we're going to take a peek at problem number 621. And 621 says, for the reciprocating saw down below here, use the relative velocity method to graphically determine the linear velocity of the blade as the crank wheel rotates counterclockwise at 1500 RPMs. Okay, so as we look at the problem here, and I'll kind of go back and forth here. Because as you know, based on the relative velocity method, we will be kind of doing some calculations and then doing some AutoCAD and then coming back and possibly doing some calculations as well. So I'm going to start out here. This is problem 621, okay? And what we're given here is we are given that the crank wheel is rotating at 15 RPMs, and they say that it's going counterclockwise, okay? So the crank wheel, as identified in the illustration here, is the circle in the middle here, okay? Now, we've already drawn the kinematic diagram for this, but I don't even know if it's the same unit, so I wouldn't even go back and try to find it in terms of like the sizes, but we did the reciprocating saw, I think back in module 1 or 2, okay? And when we showed this crank wheel, we didn't show it as a circle. We showed it as a single radius going from the center of rotation to the connection to the connecting rod, okay, or connecting link up to the slider, okay? So first things first, we're going to draw the kinematic diagram of this. Now, before we go over to AutoCAD, I'm just going to sketch it really quickly just to make sure we understand what we're going to be doing. So the center of rotation for that crank wheel is going to be considered the frame, meaning it's not moving. So we're going to use our frame symbol for that center. And then instead of drawing the wheel, we are simply going to draw the radius to connect to what will be our connecting rod. Now, we'll also notice that they do give us a dimension where our slider is going to be a 1/2 inch higher than the center of our wheel. And that dimension, again, is given in the illustration right here. So a 1/2 inch above the center of that wheel. So this is going to be my slider, and it is going to connect back to here. Okay. And then this dimension, if you would, is going to be a 1/2 inch between not the frame, but from center to center. Okay, is going to be a 1/2 inch. So it's considered, if you would, offset. Okay. Now, this 1500 RPMs, it says that we are going counterclockwise. So that means that this is at 1500 RPMs. Now, before we give it a label, we do have to number our links and letter our joints. So link number 1 is going to be the frame. Frame is here and here. Link number 2 is going to be our crank. So that means that the angular velocity of link number 2 is 1500 RPMs going counterclockwise. So that's when we can label that once we give it a link designation, which is link number 2 since it's the crank. Link number 3 is going to be the connector, and link number 4 is going to be our slider or our blade. Okay. So we'll be drawing this to scale in AutoCAD, but I just want to kind of sketch it out here so we know what we're doing, or we know what we're gonna be kind of up against. Then our lettering is going to be A, B at the end of the crank. C is going to be the center of our slider, and then D is going to be like the joint between the slider and the frame, so that's what keeps it, in this case, going horizontal. Okay. All right. So any questions right now on the designation? So we've got a standard 4-bar mechanism, crank slider mechanism. Okay. So First things first, we know we're going to be drawing the kinematic diagram, all right? Then the next thing we have to do is really ultimately we want to determine what is the linear velocity of our blade when we are in this position going counterclockwise. If we imagine pulling this going counterclockwise, do you see that we anticipate point C to move to the right horizontally because it's a slider. And this is going to be the velocity of C, point C. We don't know what it is, but we would presume that it's going to be going to the right. So we need to find the magnitude of velocity C, right? As the angular velocity of that crank goes counterclockwise at 1500 RPMs. Okay, so this is what we're ultimately going to do. Okay. So let's go ahead and draw our kinematic diagram. We don't need to put W2 in place and we don't need to put VC, but let's get our diagram in place so that we can then use it to kind of continue on in the problem. So I'm going to go over to AutoCAD right now. And I have already drawn the kinematic diagram. Now, what I'm going to do is I'm going to give you a chance to, draw yours up. I'm going to pause the video for a little bit and then we can compare, okay? Okay, so the dimensions that I have on here are not required for what you're going to be handing in for me, but they are a good verification, but kind of before moving on, because we're going to be using the geometry here for orientations of our velocity vectors, then I just like to do this double check. So since all of mine match, what I'm going to do is I'm going to get rid of these because honestly, they're kind of in the way. But again, they're good for verification. So I'm just going to do a quick file save. And I'm going to go back underneath our camera. So we've got our kinematic diagram all set, which is always step number one. So diagram, right? Diagram and making sure that it's nice and accurate. So the next thing that we're going to do is, as we know, we need to find out what is the straight line velocity of our blade as our crank goes around 1500 RPMs. Now, because these two are not directly related or directly connected, meaning that the crank is not directly connected to our slider, there's this link in between, okay? We can't do a direct method, if you would, like we did in the beginning of the chapter, meaning we can't just say, oh, at the end point, this is going this fast, which means it's going, that's what the velocity is. They're not directly connected. So we need to do what we call the relative velocity method because the velocity of C depends on the crank, but it's not directly connected to it. Okay, so it's relative to it, if you would. So the relative velocity straight line velocity equation that we use, and in its generic form is going to be the velocity of the unknown, UK, is going to be equal to the velocity of the known plus vectorially the velocity of the unknown relative to the known, okay? So this is its generic form. So we have to identify now what's unknown and what's known. So first of all, unknown is going to be the quantity that we're trying to find. And that quantity is going to be VC. So we're going to write down here, this is going to be velocity of C is going to be our unknown. It's going to be equal to the velocity of the known, although we don't know the number yet, okay? I'm confident that we can calculate the velocity of point B here, okay? And that's at the end of the crank that we know how fast it's going around, and we also know how long that is, which is 0.65 long, according to our illustration. So the velocity of B, which is going to be perpendicular, B, which is going to be perpendicular to its radius back to its center of rotation in the direction of rotation of that crank. So velocity of B is going to be our known, and we will calculate its magnitude in just a bit. Its direction is derived from here, and its magnitude is going to be using an equation that we're familiar with, okay? So that's going to be our known quantity plus vectorially. Now this one is simply going to be saying, oh, it's the velocity of C relative to B, the unknown relative to the known. Now that velocity is the straight line velocity of the link connecting these two, C and B, okay? And as we learned that straight line velocity is always perpendicular to something, so that means that it is going to be perpendicular to that link connecting these two, so perpendicular to the orientation of link number 3 right now. We don't know if it's going to go up and to the right or down and to the left, but this is going to represent the line of action, if you would, of C, the velocity of C relative to B, okay? So now if we look at each one of these, as we know, to fully define each one of these vectors, they need both magnitude and direction. And just like we did in lecture, I like to identify, what do I know for each one? So for the velocity of C, I know I don't know its magnitude, so I'm going to put like a little circle here, like that's unknown, but I'm going to put a check mark for its direction. So magnitude, I still need to find, but direction I know, okay? Is equal to. Now, although we didn't calculate it yet, I know that we know everything we need to find the magnitude of the velocity of B, which we will do next. And we know its direction, perpendicular to its line back to the center of rotation, okay? And then plus vectorial, oopsie, I don't want to put that in there. The magnitude of C relative to B, we don't know that, but we do know its direction. We know that it's perpendicular to link number 3. So as we can see here, we've got two unknowns in this vector equation, and they're separated one on either side of the equal sign. So format-wise, as far as this equation, we're in good shape. Okay, we don't have to do any manipulating or changing. So we can leave it just like this. But we do need to calculate that magnitude of the velocity of B. Now, B is on this rotating link, right? And as we learned in the beginning of the chapter, we have an equation that relates straight line velocity of any point on a rotating link and its rotational speed. And we know that to be the velocity is equal to the angular velocity of that link times the distance it is away from its center of rotation, okay? So as we look here, we want to find the straight line velocity of link B. Since link B is rotating on point B is rotating on link number 2, we are going to use the angular velocity of link number 2. And then the distance from the center of rotation out to point B is going to be that radius. Okay. So each one of these, if you would, subscripts are going to then identify the different variables. So the angular velocity 2 is what we're going to use here. But remember, we cannot use RPMs in and out of this equation. We need to be in radians per second. So we have to convert this first before we put it in this equation. So that's what we're going to do next. So kind of over on the side here, I am going to do my conversion for W2 is equal to 1,500 revolutions per minute. And I need to convert that to radians per second. So I know that 1 revolution is equal to 2 pi radians. And 1 minute is equal to 60 seconds. Okay. So if I look here, my revolutions cancel out top to bottom. My minutes cancel out top to bottom. And I'm left with radians per second. So I'm going to multiply across the top, divide by the bottom, and I will get a value for the magnitude of W2. Let me know what you get. I'll do it on the side here too, but it's always good to have shoots. Gotta grab out my calculator. Where are you? 157.08. Anybody else get that same number? I didn't get mine plugged in yet. So yep, okay, 157.07. Is somebody rounding? Go. Because I do want that second decimal place. Anybody get a 7 or an 8? Do it real quick. 100. I get 0.08. 0.08. Okay. that one right there. Okay. So we are going to use this value then in our W2. Now, the radius of B, as given in the illustration, it is 0.65, okay? So we are simply going to plug these values in, 157.08 radians per second, make sure that you keep your units in there, times 0.65 inches, okay? So we multiply these out, velocity of B, you get 102.1, and that's going to be inches per second. Double check. Make sure you get the same number as I do. Just want a confirmation. Make sure you guys are getting the same thing. 157.08. 0.65 times. Yep, you got the same thing. Awesome, awesome. Okay, I'm just gonna put a little cloud around this. I like to only box my final answers, just because this isn't a final answer, but I'm gonna use it, right? Kind of like over here. I used it in my equation, but it's not something that I'm gonna report out to answer the problem here. So this is the magnitude then. Oopsie. Magnitude of the velocity of B. And we have its direction. So with that, we are ready to, work with our vector equation here. So we're going to go back over to AutoCAD, and we're going to, use our diagram as well as this magnitude of the velocity of B to get to the velocity of C. So as we know, when we drew our diagram, we were dealing with 0.65 and 3.25. So what I'm going to do with the scaling, if you would, you'll notice that, I'm going to go back underneath here, my number is 102.1 inches per second. If I draw that to scale, then that is going to mean that in my AutoCAD, if I want to draw, for instance, my vector diagram over here, my vector diagram is going to be huge compared to this. And I want to kind of keep the fonts to be relatively in the same ballpark, if you would. So it would make sense to divide these numbers by 100. And I'm going to draw my vector, for instance, the length of vector B to be 1.021 inches long, so that when I report out my velocity later on, I'm gonna multiply by 100. So I'm dividing by 100 so that the scale of the length of the lines are going to work with the scale of the length of the lines on my layout here. So what I'm gonna do is I'm first going to change my layer to a different color, because I don't want it on the object line layer. So I'm going to put it on object 2, and I'm simply going to draw a line, okay? And I'm going to go kind of randomly out here, and I am going to set its orientation by being perpendicular, and I want to be sure that I'm on here, to that line. So it happened to be perpendicular. It's not on the line, but I just wanted it perpendicular to that line, okay? And now what I'm going to do is I am going to move this line and point to point B right here. Okay, so that it's right on point B. And now what I want to do is I want to make that a length of 1.021. Okay, so I am going to go to my circle center radius, and at the center of point B here, I'm going to draw a radius of 1.021. Okay, 1.021. So again, it's 102.1, but I'm dividing by 100 so that the scaling kind of works out with the layout here. So 1.021. Excuse me. So now I'm going to trim away the parts that I don't need. So I'm going to trim this. So now that means that the length of this vector that represents the velocity of B is a length of 1.021. And I'm going to delete that circle because I don't need it. I just needed it for the radius so I would get the length of my line. Now I know that this is pointing. Let me see here. This is pointing. Oh, I should have put it on the other side. I didn't think about it. It doesn't really matter. This is going to be pointing down and to the right because this is going in a counterclockwise direction. So let me change that. All I'm going to do is I'm going to move that vector to be down and to the right. Okay. So it's going to be actually going in that same orientation along that line perpendicular to that radius, but down and to the right. So now I am going to put my arrowheads on here so that I know that this is pointing in that direction. Okay. I'm also going to label this. So I'm going to label this velocity B. V, VB. There we go. Okay. Any questions so far? So this is the magnitude and direction of the velocity of B. Okay. The next one, if I go back underneath here, I've got VB done. Let's put on the direction for the velocity of C relative to B. That is going to be perpendicular to link number 3. So we're going to go back over here. I'm going to change my layer. And all I want to do is I want to put a line perpendicular to link number 3. So I'm going to go a line straight from here. And I'm doing shift right mouse button perpendicular to, and there we go. Okay. No arrowheads on this one. This is just setting the orientation perpendicular to that link, but I do want to label this C relative or slash B. Remember, it has to be C first, then B, because it's unknown relative to known. Okay. And then my last vector that I'm going to add here for orientation is going to be the direction for velocity of C. And we know that to be through point C going horizontal. We're pretty sure it's going to point to the right, but we're not going to put an arrowhead on it until we do our vector equation. So I'm going to go back over here, change my layer, and I'm just going to draw a horizontal line just like that. And that's just going to represent the velocity of C. Now, the line that I have in the background was just a construction line, if you would, for the offset. So you can get rid of that. You needed it when I constructed my diagram. So I'm going to say save right now. So now this is my diagram. This is going to be one of the things that you're going to screenshot for handing this in, because I want to see that you use the diagram that you created and you have it set up correctly as far as when things need to be perpendicular or in line. In line with sliders, right? Perpendicular when things are rotating to their lengths. Okay. So any questions right now on the orientations that we see here? Okay. Now what we're going to do is we are now going to set up our vector equation. Okay. So we want to start where we know the most information, and we know everything about velocity of B. So we're going to start by drawing our origin, and then we're going to put the velocity of B in place. So I'm going to go back to my object line layer, and I'm simply going to draw a vertical and a horizontal line to represent our origin. Okay, so you have to show me your origin. That, as we know, represents the equal sign. So starting on that right-hand side, I'm going to now copy my vector B with its call out. Do a copy because I want to see vector B in place here on the diagram. And then I've got to go to the intersection of these two lines. There we go. Okay. So that's VB in place. So again, do a copy so you leave it behind on the diagram. Then I'm going to go back to my vector equation, and I need to add to B the velocity of C relative to B. So I'm going to go back over here and I'm going to copy the velocity of C relative to B. I'm going to grab it using the nearest along the length here because I don't know if it's going to go up and to the right or down and to the left. Okay, so again, copy, and I'm going to put it on the end point or the tip of B using the nearest object snaps. Okay. And then the last one I'm going to put in place, I've kind of done everything I can on this side. I'm going to cross over the equal sign, and then I'm going to put my velocity of C in place. When I do that, I'm going to copy. I'm going to select, and from that endpoint, I'm going to put this right there, okay? Now, I want to find the intersection that's created. So as we can see, there is an intersection with the length of the lines I created. There is a natural intersection. So all I have to do is trim away. If you have to extend with yours, it's totally fine. So we want to get rid of the stuff that we don't need. Why is that not? There we go. Okay. All right. And now we have the lengths of these lines. The last thing we need to do is we need to determine where the arrowheads go, right? It's actually the second to last thing. We have a couple labeling items that we want to do. Now, if we go back here, we know that velocity of B, we add the velocity of C relative to B. So that means that C relative to B is going to have its tail at the tip of B and then its tip opposite. So I'm going to go back to my object 3. I'm going to add the lines. So its tail is going to be at the tip of B. So its tip is going to be here, pointing up and to the right. Okay. So that's there. Velocity of C. The velocity of C is on the other side of the equal sign. So our velocity of C, its tail is going to start at the origin and its tip is going to go to the last vector. So going back over here, I am going to go to object 4, line. So tail is at the origin. That means the tip is out here. Right about there. There we go. Now, before I do my measuring, don't forget, you have to put your vector equation here, okay? So we want to identify, I'm going to put it right about there. I'm going to double click on this. I'm going to extend this out, and I'm going to say is equal to velocity of B plus, plus vectorially velocity of C relative to B, okay? Because we want to have that equation there so we understand the arrowheads that we just did. Now, the question is asking, what is the magnitude of the velocity of C? So we know now that it's going to be moving to the right, which we were expecting it to do. We're going to go on our notes layer and we're going to do a linear distance, and our value is 0.9939. Okay. Now, remember, we scaled our values, right? We scaled them by dividing our velocity for B by 100. So that means the correct answer is going to be this number multiplied by 100. So if I go underneath here, number 4 is going to be vector diagram in CAD. Okay. And then step number 5 is our velocity of C is equal to 99 point, I forgot my number, 99.39. And our units are going to be inches per second, okay? And it is going to be moving to the right. So this is our final answer, okay? Now, we do have the final answers in our assignment. So if I go back to our course and go to module 4, and I look at assignment number 4, and I look at our final answers, and this is problem 621. Look at that. Velocity of C is, well, I got 39. I got 99.39. That's okay. 99.38 is pretty darn close. So if your numbers are like whole number one or two away, I would be concerned. But if we're one or two decimals away, I'm okay with that. Does that make sense to everybody? Okay, especially when we multiply by 100. Okay. If I wonder, I want to see, let me do this just out of curiosity. Let me go to my dimensions. I'm going to put it to a 4-place decimal. Where is that? I think it's in units. That's right. So let me go to 6-place decimal. Okay. My set as current and close. What do we get? It's 38.76. So again, very, very close here. So 39.39 is good too. So make sure when you hand this in, you're going to take a screenshot of, and it can be either separate screenshots or if you have your text large enough, if you want to do one single screenshot of the CAD work to verify the dimension of your final answer. You do not need to dimension C relative to B because it's not asking that as a final answer, okay? So it's just velocity of C or our blade, right? And then make sure that you include the work that you did to determine any values here. So writing out the vector equation, calculating for the velocity of B, converting our RPMs to radians to use them in that equation, and then what your final answer is, including the direction. Okay. Make sure that you scan this as well as the screenshots for our CAD work, and then you should be all set. So that is problem number 621, top to bottom. Are there any questions for those who are here?
Nope, makes sense to me.
No, no. Okay, good. And then I'm just going to go back over here. Notice that on 21, I gave you also the answer for the velocity of B. Okay. This is an intermediate value. And this is just to make sure that as you're calculating, you can compare that so you know that, okay, I'm ready for the next step. If you don't get that same number, and you will be showing your work for that, then that just means that, oh, I forgot something. And usually when it's a straight line velocity like this, the thing that's usually forgotten is that you didn't convert your rotational speed to radians per second. Okay, that's usually where students forget, and so that's the reason that like if you would an intermediate answer as you're getting set up, so that's there for you as well. But the final answer is the velocity at C for this problem, which is the blade speed. Okay, if there aren't any more questions, then what I'm going to do is I am going to stop our